Louis Bowen, an entropy theory for actions of nonamenable groups.
Thank you. Yeah. Thanks to the organizers the opportunity to talk. Okay, so I'd like to begin with a conjecture due to Gottschalk, which will motivate what comes next. So, just to remind everyone, so if you have a finite set and an injective map from this finite set to itself, it has to be surjective. So this is a very important, useful fact. So injectivity implies surjectivity, at least for finite sets. And Gottschalk's conjecture, he conjectured that this generalizes to cellular automata. So what this means is the following. We have an alphabet which is just a finite set. And a countable group. And we consider A to the G, just the set of all functions from G into A. And G acts on this space by just precomposition. So it's just moving we can think of this as a set of colors, then it's just moving colors around by translation. Okay, so if we have the conjecture is that if we have a map from A to the G to itself, if this map is continuous, well, there's a natural topology on this because, we just put the product topology. A has the discrete topology. So if this is continuous, G equivariant, and injective, then it must be surjective. Okay, so, well, this is still open in general. But there's a very important large special case that has been solved. So Gromov proved that this is true whenever G is a Sofic group. Okay, so it's true for Sofic groups. Okay. So Benji gave it the name Sofic. So it comes from the Hebrew word for finite. So these are kind of like groups that behave in some sense like as if they were finite. Okay, well, okay, so I'd like to define Sofic groups and then briefly sketch a proof of this statement for Sofic groups. Okay. Okay, so G is Sofic if there exists a sequence of maps Now, just a little remark here before I before I continue the sentence. These VNs, well, those are finite sets. I like the letter V for vertices because I like to think of these as graphs, as the vertex set for a graph, but that's not necessary. The symmetric group, this is just the full symmetric group on this finite set. These maps do not have to be homomorphisms. So these sigma n's are not necessarily homomorphisms. Okay, so the condition is the following. We want that the limit, well, we would like them to behave almost as if they were homomorphisms, so that in the limit they seem to be homomorphisms. Yeah, maybe I should put that here. So, okay. So if we just count the number of points for which this satisfies the homomorphism equation, this should limit on 1 for every G and H in the group. Well, that's condition number 1, but you see this condition by itself would be rather trivial. We could just send every element to the identity, and it wouldn't be very interesting. So we need one more condition, which is that we want every non-identity element to behave as if it were, as if it were a permutation without fixed points. Okay. Okay, so are the conditions, any questions though? I should, say, please ask questions at any time. I like it, okay. Okay, so these are, this is like we have a sequence of approximate actions on finite sets. And this sequence of actions is asymptotically free. Well, and asymptotically they're actions. They don't actually have to be actions to start off with. Okay, so just a few remarks. So all amenable groups satisfy these conditions because we can take the VNs to be a sequence of Fulner sets, or Fulner sequence in the group, with just the usual left translation action, well, modified appropriately to make it. Okay, also residually finite groups satisfy this because we can just have our group actually acting on finite sets in that case. It's not known whether or not all countable groups satisfy this. Okay. Any questions?
Bolshansky group, the one, the torsion, famous torsion group, satisfied?
Well, don't know. Yeah, there are a lot of groups for which we don't know whether or not they satisfy this condition. The Burnside groups, the Olshansky groups. Okay. The Higman group. Okay, so this sequence is called a Sofic approximation. So it's going to play a role in what follows. I'll usually just denote it by sigma. Okay, so I'd like to sketch a proof now of this fact. And okay. Okay, so the proof is going to go like this. And I'm sorry, I'm going to be very, well, this sketch is due to David Kerr and Hanfeng Li. Well, I'm going to sketch their proof rather than Gromov's proof or Benji's simplification. So what they did was they defined an invariant. So they said that for every continuous action of G on a compact metrizable space, so X here is a compact metrizable space, and for every Sofic approximation, there exists a number that they call the topological entropy, the Sofic topological entropy. And this number, whatever it is, it's in the interval from, well, 0 to plus infinity, or it could be minus infinity, which is a strange phenomenon. But okay. This number is a topological conjugacy invariant. Okay, so it satisfies. So it's invariant. Excuse me. Under topological conjugacy, it's a monotone under embeddings. So if y is in X is closed and equivariant and invariant under G, then the topological entropy of y is bounded by the topological entropy of X. And moreover, if y is not equal to X and X is this symbolic space, a to the G, then we have a strict inequality. Then we have a strict inequality here. And so that proves Gottschalk's conjecture. Okay, so, but I should pause for just a second. Are there any questions or,
What's the minus infinity?
Sure. So, okay, sure. So, as it turns out, this number, well, whenever G is an amenable group, like the integers, then this just agrees with the classical topological entropy. But in the non-amenable case, I will give you an example showing how this can be minus infinity. But that'll take a minute before I can get there. I'm sorry? Yes. Yes. It was proven in, I think, 1999 or the year 2000. Oh, no, it doesn't. In this case, right. G acting on a to the G is always log of the cardinality of A. It does not depend on the choice. So it's what you expect. Okay, so well, intuitively, what entropy should measure is the number of finite orbits. I guess if you're interested in hyperbolic systems, you think that entropy is counting the number of closed orbits. And it's something kind of like that. Here we have a discrete group, so we're not counting closed orbits, we're counting finite orbits. But we want to be a little bit more generous. So we want to count things that are not actually orbits, but only approximately orbits. Okay. So, if you think about what is a finite orbit, so here we have G acting on some set X, some compact metrizable space. A finite orbit would mean that we have G acting on V, where V is now a finite set, and we have an equivariant map from V into X. So that would be a finite orbit. So a finite orbit means that we have an equivariant map from V into X. Since we want to just count the number of approximately equivariant maps, we are okay with Sofic approximations. We have these partial actions on these finite sets. That's what the sophicity property gives us. And so that's what we're going to do, is we're going to look at maps from Vn into X that approximately commute with the action. Okay. So I'll remind you, we have this sequence of maps into this symmetric group. They don't have to be homomorphisms, but if you want, you can just think of them as homomorphisms. You're not going too far wrong. Okay, so we'll say that a map from the vertex set into X. So remember, G is acting on X. It's a compact metric space. And in fact, let's fix a metric. So I'll let D be a metric on X. So such a map is, I'll call it, well, I want to say, I need to qualify how good it is. Because it's not going to be exactly equivariant. So I need to say, well, it's approximately equivariant with respect to some parameters. Okay, so I'll say that it's W delta good, where W is a finite subset of the group, and delta is a positive number if the following is true. So, so I look at the distance from, so from, let me make sure I'm doing this correctly. Right. Okay, so this is a kind of L1 distance. Let me just to say again what this is. This is the I'm sorry? I'm sorry, what? Am I fixing the? Oh yeah, I'm fixing the n for now, right? Yes.
So the second G in your inequality less than delta, you're never using the energy?
No, because phi of v is in X, and G is acting on X.
Oh, all right.
Okay. Okay, so what this is saying is, to put it another way, it's saying this, where D1 is the metric. Well, it's kind of the obvious notion. So it's a metric on x to the v n that's defined by d1 of phi psi is the distance between these 2 points. Okay. Okay, so to be a good map, we just want it to be approximately equivariant. In pictures, the way you should think about this is the following. Suppose we have, we have our our finite set Vn with some, this is probably not so good. Let's just do it like this. So maybe we have our permutation that goes like this. And we map this over into X. And these 4 points inside X are not quite right. If we looked at the image of this point, it's going to have to be close to the image of this one, but it doesn't have to be perfect. Okay, so these are just approximately equivariant, and now we can define the entropy in the following way. Okay, I made a mistake, but I will fix it. Okay, so okay, so what we're looking at is, we can't count all W delta good maps because there are, typically there will be infinitely many of them. So what we're looking at is the maximum cardinality of an epsilon separated subset with respect to this metric D1. Okay, and then we take the exponential rate of growth of that, which means that we take the logarithm and then we divide by the cardinality, take the lim sup, extremize over our constants.
Then this definition W delta good is for all n equal enough.
Right, so this depends on n as well, so I probably should put that here. You could say it's a W delta n good map, if you like. Okay, so the reason why this can be minus infinity is because it's entirely possible that there are no good maps at all, in which case this is a 0, and so we get minus infinity. This actually happens in the non-amenable world. I will give you an example. So suppose, for example, that G is the free group on two generators, and that it acts on a set with 2 points, and it acts trivially. Now you think, well, the entropy should be 0. And actually, this is not the best example, now that I think about it, because the entropy is 0 in this case. So let's say it acts non-trivially. Okay, so let's say that it acts non-trivially, so A of 0 is 1, and B of 0 is 1, and vice versa. So each generator acts non-trivially. Yes, I haven't told you what sigma is. Right, so we will have two different sigmas. In one of the sigmas, I'll just choose the sigmas here to be homomorphisms. And I can form graphs, right? So if I have a sigma n, from my group into sim n, and I'm going to assume that these are homomorphisms, by the way, then I can form a graph which is just has vertices equal to the set 1 through n, and the edges will be I'll have an edge from V to where the generator sends V, and also for the other generator. So this graph, we could choose our homomorphism so that this graph is bipartite if we wanted. That's possible. That's just saying that this homomorphism factors through the kernel of this action. In that case, it's easy to see that the entropy will be 0. But we could also choose it to be very far from bipartite. In fact, we could just choose a homomorphism here at random amongst all n factorial squared homomorphisms. And it's not hard to show that that's going to be very far from bipartite, and it's going to be impossible to make anything even close to a bipartite partition, so that there will be no good maps at all, and the entropy will be minus infinity.
Could you repeat the sentence about factoring through a kernel?
Oh, so we could choose these sigma n's so that sigma n restricted to the kernel of this action. So the kernel of the action is trivial.
The kernel of this action is indexed to subgroup.
Yeah, maybe I'm making a mistake. Sorry. I am making a mistake.
If you mean the opposite, it's Z, Sn, like the image would be AN or not AN. Two possibilities. The alternating.
Yeah, so I guess what we want.
If it will be alternatable, then it will not be bipartite. If it is symmetrical, then it will be bipartite.
Okay.
You are interested in the other example.
Yeah. Okay. So this graph can either be bipartite. I guess that's or very far from bipartite. Yeah. Sorry. I'm not very good at thinking on my feet. So, but it's not a difficult thing to do. I guess what I should have said is if
Basically, basically what you have is the science model is a regular graph. If it's an expander with all kinds of values bounded, then it's not going to, you're not going to find any good match.
That's exactly what AN or not. Bipartite.
Yeah, I guess what I should have said is if the kernel of this map is contained in the kernel of the action. That's what I meant to say. Then this will be bipartite.
So for the case when x is a to the g, this is logarithm of a.
That's right. Yeah, always.
For all Sofic groups.
Yeah, that's right. Yeah. Yeah, there are cases where it doesn't depend on this choice of Sofic approximation. But it's a mystery. You know, how much does it depend on the choice of Sofic approximation? We don't fully understand. Yeah.
Are there cases where you can't fix the minus infinity changing?
Oh, yeah, sure. So G just acting on a to the G. The entropy is always log of the cardinality of A, no matter what sigma is.
So what I'm asking is that you get a minus infinity, but you cannot fix it by changing the Sofic approximation.
Oh,
But
this
here
we
it's a
don't. No.
minus infinity and you could-
This is one of the open problems. Yeah. So we don't know. It's entirely possible that for every action there is some Sofic approximation for which you do not get minus infinity. It's an open problem. It's harder than asking whether or not all groups are Sofic, in some sense. Okay, so I'd like to measure entropy. So this is the topological version. We also have a measure theoretic version. The measure theoretic version is very similar. We'd also like to count orbits, approximate orbits, but we would like to only count those that are statistically relevant. And what we interpret that to mean is that they should be approximately equidistributed with respect to the measure. Okay, so I'll say that a map is, okay, so let me go back. So now we have G acting on X mu, where mu is a G invariant probability measure. And I still want X to be a compact metrizable space, and G will still be acting continuously. So this is still a compact metric space. on which G is still acting continuously. Okay, so this time I'll say that a map is, I need to back up, so sorry. I'll fix a neighborhood of the measure in the space of all probability measures on X in the weak star topology. So this is my, the reason for, I should have left that up, but anyway, the reason for doing this is that we need to say, if we're going to say something is approximately equidistributed, we need to be able to quantify that. You know, how equidistributed is it? Well, it's equidistributed if the induced measure lies in this neighborhood. Okay, so we'll say that a map is W delta O, still with the n, good, if, well, it should be W delta n good, and if we push forward the uniform measure on Vn, then we should get in this neighborhood. So that's approximately equidistributed. Then the measure theoretic entropy is the same formula that we had before, essentially. You know, we just have one more parameter here. So it's the maximum, we're counting the maximum cardinality of an epsilon separated subset of W delta O good maps. Well, with the n as well, I guess. Yeah. Yes. It seems to depend on. Yes, it seems to, but it doesn't. So it's a theorem due to David Kerr and Han-Feng Li that this does not depend on the choice of topology or on the metric. This really is a measure conjugacy invariant. So well, the proof is essentially, well, it can be proven from Lucin's theorem. So Lucin's theorem says that if you have a measurable map from one space to another, then on a large subset, it's continuous. And that doesn't really tell you very much. You know, you have to work with it a lot. But basically, it's Lucin's theorem. Yeah, there is an equivalent definition that just uses measure theory and doesn't use topology at all. But in the interest of time, I'm not going to do that.
Moreover, you didn't need continuity of the map in this case.
Well, to make this definition, I do need that that G is acting continuously on X.
So this is not necessary. So definition of entropy is not necessary.
You're right. Yeah. I mean, it can be defined in a different way.
Yes, it was proved in our paper.
Okay. It can be defined in a different way, but without reference to topology. But this is like in practice, when you actually want to compute it, you usually have a topology, and this turns out to be a very useful definition. Okay. So that's one point. Well, another point is we're very interested in Bernoulli shifts. So when G is acting on our finite set to the G, And suppose that we have a product measure on this. So suppose that, let's say, eta is a probability measure on A, then we can consider the entropy of this action. So it preserves this product measure A to the G, and this is called a Bernoulli shift action. And the entropy is just the Shannon entropy, which I suppose everybody knows is, has this very explicit formula. So in particular, this tells us that if two Bernoulli shifts have different Shannon entropies, then they're not measurably conjugate. So this was this helps us to classify Bernoulli shifts by entropy. And let's see. I feel like I'm missing something that I wanted to write down. Well.
Variation.
Oh yeah, there is a variational principle. Okay, sure. Thank you. Okay, so there's a variational principle. So the topological entropy is just the soup of the measure theoretic entropies over all invariant measures.
But this is still for Sofic, though.
Yes.
It's not known.
Yes, it's not known what to do for arbitrary groups. That's true. Yes, there's also a notion of Sofic pressure, and there's also a variational principle for pressure.
There are no invariant measures, logical entropy.
Yes, that's right. If there's no invariant measures, then the topological entropy is minus infinity.
For any Sofic approximation? You said before you didn't know samples where
Sure.
you always had minus infinity for any Sofic approximation.
Yeah. Well, I see what you mean. Yeah, okay. You're right. So if you don't have an invariant measure, then the topological entropy is always minus infinity. That's true. But modulo that case. So if you do have we don't know. Sure. Okay, so actually I'd like to use the slides now. If I actually maybe, well, okay, that's fine. I'll go with the slides. I keep forgetting what I'm doing. Yeah, I should mention one more thing. In the non-amenable case, Ornstein and Weiss proved, well, they have this very explicit example for free groups showing that the full 2 shift over the free group factors onto the full 4 shift. So in particular, measure theoretic Sofic entropy can increase under factor maps. And I believe Brandon will talk more about this, so I want to present a different example. In fact, but while this loads up, I'll just say a few things. In fact, we can show now that for a very large class of groups, including free groups, all Bernoulli shifts factor onto each other. And also for a very large class of of non-amenable groups, we can prove that entropy is a complete invariant for Bernoulli shifts. That is, any 2 Bernoulli shifts are measurably conjugate if and only if they have the same entropy. So it's this unusual feature that we have isomorphism. Entropy is an isomorphism invariant, but it's certainly not a weak isomorphism invariant. Any questions about that? I feel like I kind of... Okay, well, let me give you another example, which is on the slide. So here we have the rank 2 free group, and we can consider the group acting on Z mod 2Z to gamma modulo this infinite cyclic subgroup. So this is, you can think of this as just all maps from our group into Z mod 2Z with the property that they are invariant under right multiplication by this one generator. So it's easy to prove that the Sofic entropy is 0 in this case for any Sofic approximation. It's an exercise. Now, we can define a map. I want to explain to you a factor map from X into the full 2-shift, which is defined like this. So we just take the coordinate at G is just the same coordinate at G, but we also add the one that's one directly north. Okay, maybe I should have a picture. So if this is the free group, and let's say that B is in this direction, it's in the vertical direction, and A is in the horizontal direction, then what this does is it just takes the number here, whatever it is, and adds the number directly north. Okay, well this is a surjective map. In fact, you can see that X is a group under pointwise addition. It's a compact abelian group. And this is also a compact abelian group, and this is a homomorphism, and it's surjective. So it takes Haar measure to Haar measure. So what we see is that we have this system which has 0 entropy in a very strong sense, and it factors onto a Bernoulli shift. And in fact, you can extrapolate this example to see that in fact it factors onto all Bernoulli shifts, not just this one, but even the infinite entropy one. Okay. Okay. So you might wonder, what can we say about things like Pinsker factors? And what can we say? I mean, in classical entropy theory, you have this maximal factor with 0 entropy, and so this is one of the problems that we've made a little bit of progress on so far. And to explain it, I need to first talk about extension entropy, which is also a new idea, which is kind of interesting. So suppose that we have a factor map. And maybe before I explain what all of this is, I should say, whenever you have a factor map, you usually consider relative entropy. You usually think, oh, the entropy of X relative to Y. This is a well-defined notion. But here we do the opposite. We talk about the entropy of Y relative to X. Okay, so what does it mean? So the entropy of Y relative to X. Well, we look at a maximum cardinality of an epsilon separated subset of good maps for the action of Y, which lift to good maps to the action of X. And that's the problem in the amenable world. All maps, all good maps from, or all, I should say maybe good maps is not so intuitive, but you should think of these as approximate finite orbits. So every kind of finite orbit for the action of Y will lift to a finite orbit for the action of X. But this is not true in the non-amenable world. So this gives us a non-trivial concept. So I didn't tell you the Ornstein-Weiss example. Let me show you the other example. The other example which I just presented to you shows that the entropy for the action, for this kind of weird action which has 0 entropy, well, the entropy for the Bernoulli shift action relative to this weird kind of 0 entropy action is 0. Because you can't have any, the entropy of Y relative to X cannot be larger than the entropy of X. Does this make sense? Yeah, please ask questions if, I know this is a little bizarre.
Does there exist an action with positive entropy and with all factor which has positive?
Yes, this is true. Yes, I'll get to that. The Bernoulli shifts have this property.
Bernoulli has no 0 factors.
Yes. Yes.
Instead of a
cyclic group, you will divide by a nonamenable group. In the free group. Then you also will get zero, or the ability of the stabilizer is the crucial.
I believe that you will also get 0. Yes. But we the reason why, so this is a co-induced action. You have an action of a subgroup, and then you can co-induce to an action of the larger group, just by putting independent copies of the action on each coset. And co-induction preserves entropy in general. So if the action of the subgroup is 0, has 0 entropy, then the action of the larger group should have 0 entropy. So it's not really a property of of the amenability of this infinite cyclic subgroup. Yeah.
Monotonicity of the entropy respect to fractal map. Can it characterize amenable groups?
Yeah, this is an open problem. It does? Oh, yeah, I forgot. I'm sorry. Yes. Yeah, Brandon has this really nice result showing that if you have any non-amenable group, okay, with any action, any probability measure preserving action, this action can be written as a factor of an action which has a generating partition that consists of only 2 parts, 2 pieces. Actually, that's okay. I guess that's a special case. Yeah, actually, okay, so you need some number of pieces, not 2, but some bounded number that depends only on the group. So you can always increase. Yeah. Right. Yeah, so for non-amenable groups, you can, it appears that you can always increase entropy under factors. Okay, so I'll go. Any more questions before I? Okay, well, I guess I'm getting close to time, so I better hurry up. Okay, so the outer Pinsker factor, or the outer Pinsker subalgebra, is the sigma subalgebra that's generated by all sets A. So that, if we have a subset A, this should just be X, I think. Yeah, this should just be X. If we have a subset A, then we can look at A and its complement in just the sigma algebra that's generated by A and the group action. And we have a corresponding factor, where the sigma algebra of Y pulls back to this sigma algebra generated by A. And we look at the factor, so we look at the relative entropy of Y given X. If that's 0, then we say that A is contained in the Pinsker, or the outer Pinsker subalgebra. And we'll say that the action has completely positive entropy if this Pinsker algebra is trivial. So this is an a priori stronger notion than saying that all actions, all factors, all non-trivial factors have positive Sofic entropy. And this notion, I'm suppressing it, but this all depends on a choice of Sofic approximation. I'm suppressing that choice from the notation, but it does. So David Kerr proved that Bernoulli shifts have this property. They have completely positive entropy. And in the remaining 2 minutes, I was going to sketch a proof with Tim Austin. I don't think I'll get to the whole thing. But it brings in some new ideas, which I think are very interesting. Okay. So if we have any metric measure space, so this will be a probability measure, we can define the concentration function in the following way. What it is if we have a subset A with measure at least 1/2, we look at its epsilon neighborhood. So that's what A epsilon stands for. And we look at 1 minus that. We take the infimum over all A. So if this is small, it means that if you have a set with measure 1/2 and you look at its epsilon neighborhood, then that's most of the space. So so for example, it's known that the that the Hamming cube has this property. It has exponential concentration with this particular rate. So it actually, I hope I'm not making them. Okay. I'm sorry. Oh, it's the soup. Oh yeah, I'm sorry. It's the soup, not the inf. Okay, so I don't have much time here, but okay, if well, whenever we have a dynamical system, let's say that S is a finite set and gamma is just acting on S to the gamma, preserving some measure mu. It doesn't have to be a Bernoulli measure. Then we have a lot of metric measure spaces associated to this. We just restrict S. We have a finite subset F, so we can just project the measure to S to the F and take the Hamming metric on this product space. And we say that this action has exponential concentration of measure. Well, intuitively, there's some technical details, but intuitively, if this sequence of metric measure spaces satisfies some concentration properties asymptotically. Okay, so the precise thing is that you want to say that there exist subsets which are asymptotically large, and these subsets union to the group, they're increasing to the group. And for any epsilon, there exists a delta, so that if F is sufficiently invariant, I'm assuming now that my group is amenable, then this concentration function is bounded by an exponential like this. Okay, so this is what's done for amenable groups. Martin and Shield proved that this is equivalent to Bernoullicity. What we did was we took this definition and we made it into a Sofic.
Sorry, for what group?
These are for amenable groups. Well, they actually prove this for the integers. And I can sketch a proof that this extends to all amenable groups. They called this the almost blowing up property. And yeah, I prefer a concentration of measure or something, just to, it's a trendy name, right? Well, there's a Sofic version. So if you're a Sofic group and you're acting, you also have metric measure spaces that are associated. Okay, this time my group is just acting on X to the mu, not S gamma, but just some space X. And we look at measures on X to the, this should be a Vn. That should be our Sofic approximation. And we also want an exponential concentration of measure. We want our measures to be supported on good maps. And we want this third property, which is a little bit, I don't really have time I only have time to give a kind of impressionistic picture. So this will be, if a vertex is chosen uniformly at random, then we need this property. So this is a kind of locality. We want a kind of local convergence, so that in our Sofic approximation, every point kind of looks like every other point, approximately. Okay, we can prove that this is a measure conjugacy invariant. It implies CPE. And it's very easy to prove that Bernoulli shifts have this property, using what other people have done for concentration. So this gives a new proof that Bernoulli shifts have this. We do. This is completely open. And it should be, because in fact, Soren Popa has examples showing that you can have factors of Bernoulli shifts where the group is a property T group, and these factors are not measurably conjugate to Bernoulli shifts. So this is another new phenomenon for non-amenable groups. Those examples satisfy this definition. So this does not imply Bernoulli, but it might imply factor of Bernoulli. We don't know.